Hey folks, in lesson 15 we're going to introduce this special case in which we use central forces and how we apply the concept of conservation of angular momentum to then describe orbital motion. Let's take a look at the definition of a central force. And this is simply a force F sub p that acts on the particle, that acts on this mass, and satisfies the relationship in which the moment of p about point O, this being an inertially fixed point, is equal to 0. Now, you can probably already recognize from our discussions that the only way to achieve this, if we've got a point O, and then we've got our mass p, the only way to achieve this is if the force Fp is pointed along the line of action between those points. And so here, Fp along that line of action, and then that would satisfy the condition in which our moment is equal to 0. Now we have a few important things to observe about this, and the first is that if the moment of point P about point O, an inertially fixed point, is equal to 0, then angular momentum is conserved. So that tells us, based on our previous derivations and discussions, that the time derivative of angular momentum as observed in the inertial reference frame is equal to 0, momentum is conserved, and so this tells us that our initial conditions are really all that matters. So if we've got this point, and we're going to be developing this orbital motion in a moment, but if we've got this point moving relative to point O, whatever our initial angular velocity or linear velocity is that we put into the system to give us our angular momentum, then this momentum, the magnitude of momentum, will be conserved. It'll be the same in the system no matter what. Now in addition, when we say that the time derivative of angular momentum is conserved, that's not only about the magnitude of the momentum, but it's also telling us something about the direction of momentum. And so if the angular momentum about point O is in this direction, then angular momentum is always going to be in that direction. So this vector is never going to change orientation. And that tells us something very important about the motion of the particle, in that it's always going to be constrained to a plane that's perpendicular to this vector. So imagine that we've got this plane that's defined by this vector, the angular momentum of point P as observed, or angular momentum of point P about point O, and so the motion of this particle P can only be within this plane. And that's regardless of where this particle P is going to travel. We're always going to have this line of action and then a central force within that line of action. So what this tells us is that any problem or any situation where we have a central force can always be reduced to a two-dimensional problem. And that's no matter what. It's going to be a two-dimensional problem, it's going to be a planar problem, and that plane is always determined by the direction of the angular momentum. And last, we'll take advantage again of the magnitude. So we said that the magnitude and direction are always the same. We'll take advantage of the magnitude being the same, and we'll be able to use this initial condition that we set in place with our angular momentum, and then we'll be able to then decouple the equations of motion with the right steps and simplify this to give us useful tools for describing orbital motion in a more efficient way. So let's develop our simple model of satellite motion. To do this, we're going to use big gravity. So gravity on this, kind of space scale. And what we're saying here is that we've got some mass, and we'll call this mass O. That's a big mass, and then we've got a little mass that we'll call mass P, which are conveniently located at point O, and point P. And then we're going to apply Newton's universal law of gravitation. And so this is the big gravity concept, in which that force, that attractive force between them, Newton defined as G multiplied times big M, so the mass of the big object, divided or multiplied by the mass of the small object, divided by r squared, so the distance between those two objects. You can see that this is a central force problem because we've got our force Fp that's going from the small object to the large object, and then also because forces have to be equal and opposite, we have that equal and opposite force Fp. Now for orbital motion, you've probably heard that this is called the two-body problem, in which we have a large mass and we have a small mass. Now, we're setting this up because we're only dealing with a single particle, and we're only going to do our dynamics on this single mass, the small mass. That the way we're setting this up is that we're saying that our big object is inertially fixed. So this would be like the sun, that's inertially fixed, the earth that's rotating around the sun, or if we assume that the earth is inertially fixed and the moon rotating around the earth, or an even better situation would be if this is just a smaller satellite. But in reality, this larger mass is not inertially fixed. So right now, we're making a very simple assumption, assuming that it's inertial, and so this isn't really a two-body problem yet. We will tackle this in a couple weeks when we start dealing with multi-particle systems, and we'll develop the equations for a two-body problem. So we don't confuse things, I'm going to take off the force that's applied to the larger mass because we're only dealing with the smaller mass, mass P. But remember, we still do need to have our mass of our larger object because of Newton's universal law of gravitation. So let's apply our reference frames. We'll have an inertial reference frame. And for our inertial reference frame, we'll have E1 that's pointing to the right, so it's along the line OP, when theta, so we've put in a coordinate theta, is equal to 0, and then E3 being out of the page or out of the plane of motion, and then E2 defined as the cross product between the vectors E3 and E1. And then let's add a polar reference frame. And the polar reference frame defined by three vectors E sub r, E sub theta, and E sub z. E sub r along the line of OP, E sub z the same as E3, and then E theta being the cross product of EZ, ER. And then because we're using a polar frame, we need to add in another coordinate that we'll call r, being the distance from point O to point P. Our kinematics are well defined for our polar frame, in which we have our position vector being r in the ER direction, velocity of P as observed in the inertial reference frame is equal to r dot ER plus r theta dot in the E theta direction. And then our acceleration, P with respect to O, as observed in the inertial reference frame, is r double dot minus r theta dot squared in the ER direction plus r theta double dot plus 2 r dot theta dot in the E theta direction. And so the next step is to apply Newton's second law, which is Fp is equal to mp multiplied times the acceleration of p with respect to O as observed in the inertial reference frame. We need to define Fp, so that means we need a free body diagram. And for our free body diagram, is our particle, and then we have a vector Fp applied to the particle. Now the vector Fp is always going to be directed toward from the small mass. Okay, it's on the small mass and it's directed toward the large mass. That's the gravity that small mass is experiencing. So, on our free body diagram, Fp is going to be equal to minus g, our gravitational constant, the mass of the large object multiplied times the mass of the small object, r squared, and the direction is in ER. So the direction is in the negative ER direction. So let's plug all this into Newton's second law, and we'll get negative g mo mp divided by r squared in the ER direction is equal to the mass of point P multiplied by the acceleration, which is r double dot minus r theta dot squared in the ER direction. Let's move this out of the way. Then plus the mass of point P multiplied times r theta double dot plus 2 r dot theta dot in the E theta direction. And so if we equate our coefficients in these different directions, in the ER direction, we get minus g mo mp divided by r squared is equal to mp r double dot minus r theta dot squared. And that gives us one of our equations of motion. R double dot is equal to negative g mo r squared plus r theta dot squared. So then if we look in our E theta direction, these coefficients give us, on the left hand side there's no force in the E theta direction, and this is equal to m r theta double dot plus mp, that has a p on it, multiplied times 2 r dot theta dot. So this gives us our second equation of motion, in which we have theta double dot is equal to negative 2 r dot theta dot divided by r. So let's focus in on these equations of motion for just a moment. We have two ordinary differential equations, two second-order ordinary differential equations that govern the motion of this system. Now notice that these two equations are coupled together, so which means that they're sharing terms. We've seen this before in other systems. So in our equation of motion, for our second-order term, for our position, our radius, we have a theta dot that's in there, but we also have our r terms in there as well. So that's where it's coupled together. Our theta double dot is also coupled. We have r terms within our theta equation. And so that means that we need to solve these equations simultaneously. We've done this before numerically using ODE 45, or we can put them in matrix form. But recall that we're going to use the fact that this is a central force system to be able to simplify these equations. So when we have a central force, angular momentum is conserved. So that means that the initial conditions tell us everything we need to know about its motion unless it's acted upon by some force other than the central force. So as long as we've got just the central force, let's use this fact of conservation of angular momentum to our advantage. So let's start by calculating angular momentum. So the angular momentum of point P about the inertial point O is equal to r p with respect to O crossed with the mass of P multiplied times the velocity of P with respect to O as observed in the inertial reference frame. This is r in the ER direction crossed with that mass multiplied times our velocity, which we pull down from the top. So it's r dot in the ER direction plus r theta dot in the E theta direction. And then this gives us the vector m r squared theta dot, and this is in the EZ direction, because when we cross ER with ER we get 0. When we cross ER with E theta, that gives us EZ. So we've confirmed what we said earlier, which is that the magnitude and the direction of this are never going to change. So the magnitude of our angular momentum is conserved, as well as the direction, which is always going to be in the easy direction, so it's in planar motion. But there's another very important thing that comes out of this, in that the magnitude is only dependent upon two things. The magnitude is only dependent upon this radius r, or length r, and then theta dot. So instead of it being dependent upon r dot, theta, and theta dot, the full state of the equation, there's only two parameters that we need to be concerned about, and that's the distance away from the larger mass and then the angular speed. And so we can just say that the magnitude of the angular momentum is always going to be equal to the mass r squared theta dot. So with this in hand, let's define a new constant scalar, or that we'll just call HO, which is going to take the magnitude of our angular momentum, which we know never changes, it's constant, and divide that by the mass. So this is a way of normalizing that angular momentum, and we call this the specific magnitude. The specific magnitude of the angular momentum. And what we get here is mp r squared theta dot divided by mp, and this will be r squared theta dot. And so with this specific magnitude of the angular momentum, we now have something that's transferable between systems. This is something that is independent of mass because we've divided mass out. And so let's take this and let's plug it back into our equations of motion. And so we have HO, which is equal to r squared theta dot. If we solve for theta dot, then we get our specific magnitude of the angular momentum divided by r squared. And let's plug in theta dot into each of these equations of motion. So for the first equation of motion, which is theta double dot, is equal to negative 2 r dot theta dot divided by r. We plug this in, so we get negative 2 r dot h naught divided by r squared. And so theta double dot is equal to negative 2 r dot h naught divided by r cubed. There's our first equation of motion. And then for our second equation of motion, r double dot being equal to negative g mass at point O divided by r squared plus r. Substitute this in, so h naught divided by r squared all squared. And so r double dot is equal to minus g, the mass of O divided by r squared, plus h naught divided by r cubed. And what we get out of this is that the equation of motion, this differential equation that governs r, is now completely uncoupled from theta. Notice there's no theta terms in here, it's only based on r's. Our HO, the specific magnitude of the angular momentum, is equal to r squared theta dot, and that's an initial condition. Okay, so once we set that into motion, given an initial distance away from the first mass and an initial theta dot, that's a constant property. So this isn't changing. And so this allows us to make good interpretations now. So let's show this with a couple cases. Now I should also point out that theta double dot is still a coupled equation. Okay, so we inserted this HO, our specific magnitude of the angular momentum, which is true, at all times during this trajectory because of the conservation of angular momentum. But we still have theta double dot that's reliant upon the state of r, so r and r dot. So let's look at these cases using these equations. So case 1 is going to be where we have HO is equal to 0. And the only way that HO can be equal to 0, our specific magnitude of the angular momentum, is when theta dot is equal to 0. Okay? Because H naught is equal to r squared theta dot. Now, we can't set r equal to 0 because what would happen here is that this will blow up because this is in the denominator. But if theta dot is equal to 0 and our specific magnitude is equal to 0, then r double dot is equal to negative g mo divided by r squared. And if all this is equal to 0, then that term is equal to 0. So now the equation of motion in the r direction for the r coordinate is simply equal to this term that includes our gravitational constant, our mass, and then is dependent upon r squared. And so what we're saying here is that the acceleration of that particle p, or of that mass p, is going to be accelerating straight from the small mass is going to be accelerating straight into the large mass. And then they're simply going to collide. Oh, also, the theta double dot is equal to 0 because if we set h naught equal to 0, that term goes to 0 as well. So this is the same as just taking an object and then just dropping it from the small mass into the large mass. If you dropped a baseball, just held it up in the air and dropped it onto the ground, this is what we're getting. For our next simple case, case number 2, is going to be if we have steady state motion. So steady state is going to be where r double dot is equal to 0, no acceleration, and theta double dot is equal to 0 as well. And so if we plug these two in to our equation of motion, then we get 0 is equal to minus g mo divided by r naught squared plus ho squared divided by r naught cubed. And the reason why we're using r naught is because we have a steady state condition, so this is going to be now a constant based on that radius, the initial radius that we give it. And so we rearrange. So we get g times the mass of the big object divided by r naught squared is equal to, and let's plug in the actual terms for our specific magnitude of the angular momentum, and so we'll get r naught squared multiplied times theta dot, total quantity squared divided by r naught, and then this gives us theta dot is equal to g multiplied times the big mass divided by r naught cubed, the square root of the entire piece. And so from this, we see that we have a constant radius, r naught, and then we have a constant speed due to our steady state condition. And so this is describing, if there's our big mass O, this is describing a circular orbit of our small mass P. And it's a circular orbit that has a constant speed, or constant velocity. And so that velocity, when we plug that back into our expression using our polar frame, in the inertial reference frame, is equal to our initial radius, g times mo divided by ro cubed, and square root of the entire thing, in the e theta direction, okay, which is the tangential direction that we see here. So this is the velocity of p with respect to o as observed in the inertial reference frame. So hopefully what you're seeing here is the importance of this parameter, which we're calling the magnitude of the angular momentum, or the specific magnitude of the angular momentum, because this specific magnitude of the angular momentum is going to tell us, based on how we parameterize this, how the system is going to behave, because it's going to conserve that magnitude. Now these two cases, one which we're just dropping the mass, and then the other in which we have steady state, a circular orbit. These are rather simple cases, but if you know anything about orbital motion, or if you've seen this before, you know that not all orbits are circular. In fact, most orbits are not circular, but instead they're elliptical. So we would take those equations of motion, and we would develop the equations so that they would be able to tell us more about what's called the eccentricity of the orbit. So if it's not circular, it's eccentric, and so you can solve those equations of motion. So there are two tutorials, tutorial 4.2 and 4.3 in the book, that solve for those equations of motion. There's a clever transform in which we're able to get harmonic motion, which we've solved before, to be able to understand that. And so I encourage you to look to those tutorials. We're not going to go through those in depth here, but I do want to give you an overview of what those orbital mechanics look like. So in fact, we could spend an entire chapter on orbital mechanics and an understanding how all this works. But let's just take our mass, and this is our big mass, in which we have our particle floating around it due to our central force of gravity. And the first thing that we did is we said, all right, let's make a circular motion. Most orbits aren't circular. Okay, this was first discovered or first observed by Johannes Kepler, and then this type of motion we considered having an eccentricity. Okay, and if you read through that tutorial, you'll see where this shows up. But an eccentricity of 0. Now, if most orbits aren't circular, then they have another shape. And so the common shape that we tend to think of is an elliptical shape. So this shape, this elliptical shape, these are governed by this same E, this eccentricity parameter, in which we have an eccentricity that varies between 0 and 1. So being less eccentric, okay, more like a circle, then more eccentric, more like this elongated ellipse with a long major axis. All right, next we have a parabolic orbit. And so a parabolic orbit would have an eccentricity of 1. And so on a parabolic orbit, you can see here that this is a particular value. Our circular is a particular value. We have a range for our elliptical orbits. But for our parabolic orbit, what we're saying is that this body that's traveling along in this object, or traveling along in this orbit, is going to leave this gravitational field, but always going to slow down with relationship to the gravitational field. So theoretically, this orbit is going, or this body is going to move away, and then it's going to eventually stop, and then never return. Then there's one more orbit, and that's a hyperbolic orbit. Put that in hot pink. And so for a hyperbolic orbit, we have the eccentricity greater than 1. And so any object that's traveling on a hyperbolic orbit is going to have an escape velocity. So it's going to leave and never return. We tend to think of this as asteroids that would come into a gravitational field, and it has such a large velocity that it's going to escape the velocity and then move away from that gravitational field, and then certainly never to return. So let's continue with understanding these orbits, and let's talk about how we can use angular impulse to transfer between one orbit to another orbit. So let's say we're on this orbit 1, So orbit 1. And we've got another orbit. Both of these being circular orbits as we've drawn them here. And so our goal is to transfer our mass from orbit 1, in which we're in a nice steady state condition, to orbit 2, in which we can be in a steady state condition there. And so we want to be able to apply or fire our thrusters or add those conditions in order to make those transforms. So what we're going to do is we're going to apply 2 angular impulses to make that happen. So remember that when we're in orbit 1, our angular momentum is conserved. And so we have this for orbit 1. And we can't go directly from orbit 1 to orbit 2, but instead we need to put ourselves into another orbit, which we'll call a transfer orbit. And this transfer orbit connects these 2 orbits together. So to make it to a transfer orbit, if we've got our first orbit, we now want to get into our steady state into our transfer orbit, then we need to add to this an angular impulse. And this angular impulse will occur over a very, very short time, so time 1 to time 2. And that's what's going to get us from orbit 1, we apply an angular impulse to get us into our transfer orbit. And so how this would look is that if we're on this trajectory on orbit 1, and we get to this point, it's at the bottom, or what's the bottom to us, and we apply our angular impulse over that very short time, time 1 to time 2, and now our impulse has given us new velocity, and so we're tracking along now into our transfer orbit. And so as we go along our transfer orbit, which is elliptical, then we want to, once we've joined paths with orbit number 2, we now need to apply another impulse to put us into orbit 2. And so our second impulse is going to be applied when we're in this steady state condition for our transfer orbit. We're going to add to that an impulse, p with respect to O. We'll call this from time 3 to time 4. So there's where we're going to apply our impulse, p with respect to O, time 3 to time 4. Okay, it's an impulse, so it's a very, very small time window, and we'll be changing our velocity to put us into the tangent to orbit number 2. And then from that, we should be able to get us back into steady state of our angular momentum in orbit 2 now. So now, being in orbit 2 and staying there because we're conserving angular momentum until it's acted upon by another force, another impulse. And so this has a name. It's called the Hohmann transfer orbit, is what this transfer orbit is called. And this Hohmann transfer is, as far as we know, the most efficient way to change between one orbit to another orbit by introducing this transfer orbit simply by adding momentum here, or having an angular impulse, and then adding momentum at another point to put you into that second orbit. So hopefully this provides you an interesting example in which you would apply an angular impulse for a very practical purpose. This stuff's used all the time. And then also just kind of give you an idea of where you can go with some of these concepts of angular momentum, where we started out with linear momentum. Remember that Newton's second law is wrapped up in all of this, which was the foundation for it all. All right, that concludes this lesson, and I'll see you in class.